So I timed myself a couple of times doing this talk. I think I should be able to keep to time, but yeah, I do have a bit of a tendency to go off on tangents. So hopefully, try to rein me in if I start to go off. To save time, I was just going to kind of very quickly skip through the about me slide because it's not super important. Stuff. The relevant thing that is probably important for this talk is the leucine part. I really like leucine. I've been working with leucine for 13 years. It's very near and dear to my heart, and it's very relevant for this talk. And the labradoodle's name is Louis. So, about this talk. Yay, Louis! So, what am I going to talk about in this talk specifically? This is going to be a fairly deep dive into some fairly significant performance improvements that we've worked on and delivered in the past year. I'm planning to get into some leucine internals. I'm planning to go fairly deep, but don't worry if you're not familiar with leucine, because I'm going to try to introduce everything before I talk about it. So it won't just be like throwing you into the deep end. It'll be sort of a gentle walk into the deep end. The key takeaway that you should probably get from this talk is that you can really speed up your searches if you take advantage of the way your data is stored, which may be obvious, but I'm going to go through some examples of how we did that specifically. Now, before you can improve anything, you need to know where you are, right? You need to be able to measure where you are and how you're doing to actually see if you're getting better. A lot of what we did, sort of started off as quick and dirty prototypes, where it was like, okay, maybe this will work, and then quickly implement it, run a benchmark. If the benchmarks get better, great. Let's productionalize it. Let's actually clean it up and do a real implementation that can pass code review. So to do that, we use benchmarks. We have on the OpenSearch.org website, we have nightly benchmarks. Go check these out. Not right now, please pay attention to me. But after this talk, go check out the OpenSearch.org nightly benchmarks. We specifically have these two GitHub repos. The first one, the OpenSearch benchmark repo, that's where the actual benchmark code lives. It's written in Python. If you want to make contributions to it, please do. We always appreciate contributions. And then the second repo is the benchmark workload. So it actually defines what the benchmarks are. We've had several benchmarks that we've been running over the years. NYC taxis is a log of New York City taxi rides from some time period. HTTP logs is logs from a web server during some World Cup, I think. And then there's one called PMC that I believe is a medical journal corpus. Like I've gone through some of the documents and they look like medical journal articles. So for the purposes of this talk, I'm going to focus on the Big 5 workload. Now, this is a benchmark workload that was originally published by Elastic, and they under the Apache 2 software license. And so, it's a really good benchmark workload that covers a variety of queries, aggregations, sort of useful things for people using OpenSearch. And so, as written, it didn't work perfectly for OpenSearch, so we had to tweak it, and we imported it into the OpenSearch workloads. We now have it on our nightly benchmarks. Again, after this talk, go check them out, see how we've been doing on Big 5 over time. So let's get into the stuff that we improved. So the first major area that we decided to target was text queries. So we were a little confused about this, that OpenSearch, the performance of OpenSearch on the Big 5 text queries wasn't great. which was really weird. Lucene does text queries like that. The underlying Lucene library, that's what it was built for. It was built to handle text queries very fast. So why were we slow, right? Like we don't do anything clever. We just hand them off to Lucene. Well, so it turns out that the Big Five workload was running, for its text queries, was running some fairly simple, multi-keyword searches over this field called message. So we looked into it. And it's like, well, how was the message field defined? So on OpenSearch, as you can see, looking at this mapping, it has type text, just a regular old text field. Well, and again, we got this benchmark from Elastic, and we saw that for Elasticsearch, they were using this thing called a match-only text field. We're like, what? Match-only text field? What's that? So it turns out that a match-only text field, it's very similar to text, except that it, among other things, it doesn't store frequencies or what are called norms. Norm is really just a fancy way of saying document length. So why does this matter? Well, it matters for scoring. So, of course, when you're doing text search, usually you want to surface the most relevant results. Well, how do you define relevance? Well, the way that Lucene does, and therefore OpenSearch does, is with the BM25 formula. I want you all to memorize this. There will be a quiz at the end. No, I'm kidding. Actually, the BM25 formula, the only real thing that you have to pay attention to is, I'm going to point over here. So, like this, K1 is a constant, B is also a constant, the average document length is a constant, and the IDF, that's not a constant across the terms. So IDF stands for inverse document frequency. So it's a property of the search term, but not a property of the documents. In fact, the only two terms that relate to the current document, so to score a document, are this one, the FGD, FQD. So this one is the frequency of the term in the document. And then this length of the document, that's the norm, right? So the two things used for scoring a document are frequencies and norms, which match-only text fields don't have. So in other words, you can't actually do relevance scoring with match-only text fields. Well, why is this significant? Well, it turns out, actually, we could just speed up these text queries by simply disabling frequencies and norms, right? So then there's no scoring. What was happening was OpenSearch was actually trying to go through these millions of matching documents to find the 10 best documents, right? And so it has to keep going. It can't stop, because for all it knows, the next document could be better, could make its way into the top 10. So it had to run through all of these millions of documents. Meanwhile, if you can't do scoring, you can really collect any 10, like, say, the first 10. So instead of collecting millions, you collect 10 documents, which I hope you can appreciate is faster. So we could have just gone with the whole, let's, for the purposes of the benchmark, let's disable frequencies and norms. But we're like, well, no, let's actually give people the match-only text field. It's useful. So Rishabh implemented the match-only text field late last year. We merged it January 2nd. I think it made it into OpenSearch 2.12, I think. So yay, adding features as a result of performance work. Now, the bulk of the Big Five workload that we improved related to aggregations. Now, if you're not familiar with OpenSearch aggregations, they're essentially a group by. You have a query, the query matches some documents, and then what you do is you look at some attributes of the documents and count how many documents have some attributes. And usually the way this works is you run the query, you get the matching documents. For each matching document, you go and load these attributes from something that Lucene calls doc values. And then based on the doc values, you figure out which buckets the document lands in. And then you just increment the counts of those buckets. So, yeah. This is basically what I just, oh, yes. And the key point that I forgot to mention, my little spiel there, is that the latency of aggregations tends to scale with the number of documents that matches the query, because, of course, for every one of those documents, you have to go do these attribute lookups. So what we did was we kind of realized that we could flip that around and do it the other way. What if, instead of going from documents and figuring out which buckets the documents land in, what if we could start from the buckets and very easily say how many documents are in this bucket directly? So that's what we did. And I'm going to walk you through some examples. So we started with, I'm going to start with range aggregations because it makes sense for the context of this talk. This is actually chronologically, I'm sort of retconning here that this isn't the order in which we did things, but I think it flows better. So a range query, a range aggregation. I'm not sure how readable the slide is. You typically use them, say you're running a product search website, and you want to show people for the product matches how many products are in each price range. You could do that with a range aggregation by specifying aggregation buckets for each price range. This particular example comes from the OpenSearch documentation. And it covers, it's looking at logs and seeing how many bytes, were in the response from, I think, HTTP logs. So this is the response. As you can see, for each range, we get how many documents landed in each bucket. Well, how can we do this directly? Let's look at how Lucene stores numeric fields, like the size in bytes. So it uses what's called a block KD tree or a BKD tree. So these trees tend to be built bottom up. The key thing is that the leaf nodes, where's my pointer? Oh, I lost my pointer. Okay. So the leaf nodes, if you look at the bottom left, they tend to have 512 documents. They fill up until they have 512, and then they'll potentially spill over into the next leaf and the next leaf and the next leaf. And then meanwhile you create these parent nodes that join the leaves. And it ends up actually being a binary tree. It's not strictly specified, but it just happens that it ends up being a binary tree. So these parent nodes, and the reason why I use the difference between squares and rounded edges. The parent nodes don't actually store any documents. They're purely structural, but they do store some metadata. Specifically, they store the minimum and maximum value in the subtree, as well as how many documents are in the subtree. This is going to be important. So let's say we want to directly count how many documents are in the 1,000 to 2,000 range. Well, what we can do is we just kind of look down in the tree and see where would 1,000 live. Well, it would live in the second leaf node, and then 2,000 lives in this third leaf node, and then fourth leaf node, and the third leaf node in between is entirely within the range. So we can directly count the number of documents in this range by diving down into that first yellow leaf node, scanning through until we hit 1,000, and then starting from 1,000, because these values are, the documents in the leaf are sorted by value. Then we start counting documents. The green leaf node, we don't even have to visit it. We just look at it and say, yep, that's in our bucket. And so we just add 512. And then with the final leaf node, we run through it until we hit 2,000, we stop counting. There we go. We've efficiently counted how many documents are in the range. Now this gets even more efficient when you've got a bigger range or more documents and therefore more leaves. So let's say we're counting 1,000 to 4,000. I hope you can see that, each of the green nodes here is entirely within that 1,000 to 4,000 range. And so we can just count them, right? Just read off the counts, add them to our bucket count. And I hope it's clear from these two examples that at most, you only ever need to scan 2 leaf nodes, right? I think we can all see that, yeah, you'll never have to at least iterate through more than 2. The one at the beginning, one at the end. Everything else is going to be entirely within the range, and yeah, you just add it in. So yeah, that was the implementation that we did, and yeah, we were able to speed up range aggregations. Nice. Now, moving on to date histograms. It's like, well, what's a date histogram? It's essentially saying, like, okay, it's similar to a range aggregation, but instead, for this case, it's specifically on a datetime field, and your ranges tend to be, hours, days, minutes, weeks. Yeah, so they're sort of a fixed width, and yeah, you're going to see how many points land within each of those buckets. I like to think that date histograms really are essentially range aggregations in disguise. And the mathematician in me would like to say, well, we already solved range aggregations, and so we can just refer to the earlier solved problem, and we're done. Now, in truth, it actually happened the other way around. Ankit, who's sitting over there, he actually improved the performance of date histogram aggregations all the way in November of last year. Like I think you saw that Bowen sped up the range aggregations just 2 months ago. So we could have done it the other way, but yeah, this is just how things worked out. Plus I think Ankit was correct to focus on date histograms because they are probably used more. People, it's very relevant when you're dealing with time series data. Like if you want to graph how many things happened over time, you're going to want to use date histograms. So there was, we did run into a slight problem though with date histograms and using this approach. It works great when you've got a small number of these ranges that, for each range you just dive into the tree and count. But when there's a lot of buckets, we're talking like thousands upon thousands of buckets, doing a visit down into this tree, and especially the part of like visiting these leaf nodes, like visiting these partial leaf nodes, that gets kind of expensive. And it can actually get a little bit slower than the old school, like just iterate through the documents, count the doc values. So we temporarily, ended up disabling this particular optimization when the number of buckets was, I think it was more than 1,000. I think we set a threshold of 1,000. If there are fewer than 1,000 buckets, go for it. If there's more than 1,000, be like, no, just fall back to doing it the old way. But we're like, we want to be cleverer about this. We want to, we still want to be able to handle these like thousands of buckets. So the trick that we came up with was like, hey, what if we just do one traversal, like just walk through the tree from left to right, focus on a bucket at a time, because these buckets are bounded in time and the tree is sorted by time. And so, for the current bucket, you're just counting up documents, and then once you hit a value that hits the right endpoint of your range, you just flip to the next bucket and keep counting. You could still take advantage of the whole thing where, like, if an entire leaf or parent node fits within the current bucket, you just count it, right? You don't have to visit anything, which is cool. So yeah, Bowen implemented that back in May. So I do have some benchmarks handy for this one. Again, I'm not sure how readable it'll be for you in the audience, but the key thing, if you look at the lower ones, the per minute aggregations got 1,000 times faster. Now, I don't recall if this is comparing against the slow, like trying to dive down and visit the tree for each and every minute, or if it was the vanilla just iterate through the doc IDs. But regardless, what's actually even cooler, I think, is the top numbers, where for the per hour aggregations, we had seen improvements with doing the dive into the tree for each hour, but then doing this sweeping thing, we got another 6 to 8 times faster than that, which was pretty cool. There are some caveats, though. Alas, there is no free lunch. So these optimizations don't apply when there are deleted documents. And this is because when you delete a document, Lucene doesn't delete it right away. It actually just marks it deleted in a separate bitmap, a bit set. And so that deleted document is still in the tree, and so your counts would be off, right? That you would be counting deleted documents. So to be safe and give people the right answers, we disable the optimization if there are deleted documents. But we do go per Lucene segment. So Lucene has the segmented architecture. I'm going to get into that later. But if one segment has deleted documents, we skip it for that segment. But if all the other segments don't have deleted documents, we can still optimize them. So you still get most of the benefit. We also can't use them with sub-aggregations. That when you have an aggregation underneath another aggregation, it's hard to count the intersection between them. The exception is if, say, you're doing like a per hour aggregation, then underneath that you're doing a per minute. You could do a sweep and count up both buckets, so that's okay. Also, usually this only really kicks in when the top level query is a match all. The exception is, again, if you have a range query over your date time field, say for a date histogram, you could still use that, and it just kind of chops off the beginning and end of your ranges. So let's move on to terms aggregation, where we did a similar kind of thing. So terms aggregation, think, for example, what my go-to example is you're searching a movie database, and for your search, you want to know how many matching movies are comedies, dramas, horror, etc. Right? Again, I ripped this example from the OpenSearch documentation. In this case, it's searching logs and doing a terms aggregation on the HTTP response. So, as one would expect, you've got a lot of documents that are happy 200s. You've got a few matches that are 404s, and then an even smaller number that are very unhappy server failure 503s. So, how does Lucene store the keyword fields? Well, we're going to get into what are called terms and postings. So, there's the field itself, which exists at some offset within a file. For the field, you've got all of the terms, which are stored in a dictionary for easy lookups. And then for each term, you have what are called the postings. The postings refer to the doc IDs that match this term. And so if you were querying on this term, you would seek to the field, find your term, and then say, okay, these are the doc IDs I need to step through. If this were a text field, the postings would also, for each document, have positions, but this is a keyword field. We don't have positions. Like, everything's just in one spot. On top of that, though, per term, you also have statistics, specifically the document frequency of the term. The document frequency is how many documents have this term. Now, depending on whether you could make out the previous slide, these numbers might look familiar. These are our bucket counts. So rather than having to iterate through all the matching documents and look up this field in the doc values and put things in the relevant bucket, we could just look at the terms, and for each term, ask what its doc frequency is. And that is exactly what Sendesh did back in March. And so yes, this each of these, it's amazing how when you go from an algorithm that's essentially ON to O1, you get some pretty crazy benchmark improvements, like 100x, 1000x. So this was another one of those. Yeah. But again, before I go on to sorting a range query, I need to also say same caveats apply as for range queries, unfortunately, that if you have deletions, you can't do this trick because you would overcount. It's tricky to do it with sub-aggregations because, you need to get the sub-bucket counts. And again, it tends to assume that the top level query is matching everything. So moving on to sorting and range queries, this was an area where like we were like, oh yeah, we're totally going to invest in these. They're because yeah, this is an area where we could do better. But then they kind of got better on their own, and we were a little bit surprised, a little bit confused. We didn't really have a very good explanation for it. But luckily for us, somebody else explained it for us. So this guy, Anton Hagerstrand, has this blog at blunders.io. I definitely recommend reading this guy's blog post. Here's the link. He's written a whole series of blog posts looking at the Big Five benchmark specifically, and he's done some really deep dives. Again, long read, totally worth it. Again, after the talk. So basically, what he mentioned in that last blog post was this comes down to some finicky stuff with Java's just-in-time compiler and inlining. So the basic idea is, say you have a Java interface and you have one class that implements that interface. Any method call on that interface can be inlined by the just-in-time compiler, because it's like, oh, well, there's only one implementation. Anytime someone does a call to one of these interface methods, I'm just going to go take this class's implementation and just inject it at the call site. Cool, inlining. If you have two implementations, it'll say, oh, you know what? I'm going to inline both of them and just separate them with an if-else clause, or like an if-else statement. So, go this way or go this way. But as soon as you have three or more, what kicks in is called megamorphic dispatch, which I'm not totally positive. Like I didn't entirely understand Anton's blog. It's very dense. But my vague understanding is that it probably involves jump tables, right? That it has to do a table lookup and say, okay, I'm going to jump here and then jump to the right place. So it turns out actually that the changes that we did for the date histograms and possibly the range aggregations, we ended up removing a third implementation of Lucine's BKD visitor. So this thing visiting the tree. Lucene has this one special case where it's like if you're doing a range query that matches a lot of stuff, it'll actually invert it and find like not matching the other stuff. And so we bypass that call path. So we dropped from 3 implementations back down to 2, and so things got faster. Now, I'm pretty sure that when we added that really clever like walk through the tree counting the buckets, that was actually a third implementation of this interface. So we may have again kind of slowed things down potentially, but we didn't actually see that because this Anton Hagerstrand guy, in addition to writing awesome blog posts, he also follows it up by contributing to Lucene. So he opened this PR with Lucene, back in March, where he kind of fixed the megamorphic call problem. Not directly, because his argument was in any real application, not just benchmarks, in any real application, you're going to have 3 or more of these things anyway, right? So, what we should do is make the megamorphic calls cheaper. So what he did was this megamorphic function was getting called for every single matching document in the leaf nodes. He was like, nah, just do it once per leaf. Pay that cost once. And then for the 512 documents in the leaf, just now just run through some other part of the code, right? So he managed to cut the number of megamorphic calls by a factor of 512. At which point they're not a big deal, right? Like having a lot of megamorphic calls is bad. Having a lot divided by 512, not such a big deal. Oh, I need to hurry up a bit. So, we did do one other improvement related to sorting and range queries. I'll try to get through this one a little bit faster. Lucene has the segmented architecture, as I alluded to before. Documents come in, writer threads buffer them. They periodically flush them as these immutable segments. Periodically, segments get merged because otherwise, the number of segments would grow, and search time would grow linearly with the number of segments. That's because each segment is almost like its own standalone mini index, right? And so you'd have to iterate through all of them and say does this mini index match? Does this mini index match? Etc. So. This is a picture that I actually borrowed from another presentation, but it sort of gives you an idea of how segment sizes are usually arranged. And the default merge policy that Lucene uses will find segments of similar size and merge them together, regardless of where they are in the segment ordering. Normally not a big deal, because segment ordering for most use cases doesn't matter. However, when you're doing logs, segments tend to contain documents that are ordered chronologically because that's how the documents were written. They were written chronologically because that's how time works. When you grab a segment from over here and a segment from over here and decide to merge them just because they're the same size, you're grabbing two very different regions of time and smushing them into one segment. Whereas what Rishabh, who did the match-only text field, also did, he added an index setting to allow people, when they're doing log-based workloads, to change the merge policy so that it will only merge adjacent segments. So this means that temporarily co-located documents will stay temporally co-located. And it means that each segment will have a disjoint range of time. Right? Which then means that if you got a range query, you could just easily look at a segment and say, does this segment intersect my range? And if it doesn't, you just skip it. Similarly for sorting, once you've got your top n documents sorted by time, you can just glance and say well, will this range give me something better than these top 10? And if it won't, skip it. So yeah, this was a nice improvement as well. So I'm very, very quickly going to touch on some future work that we've got in progress and will hopefully be delivering soon, or in the coming months. So one area where we've seen some improvement is networking. That OpenSearch right now for node-to-node communication and for client-to-server communication, that the serialization formats aren't necessarily the most efficient. Especially for the client-to-server, there's this hand-rolled JSON parsing. We've seen some preliminary numbers suggesting that switching to something like protobuf and gRPC, there are engineers at Uber actively working on this, and they've shown some promising results. It's pretty exciting. I mentioned before with the various aggregations, it's it doesn't work with sub-aggregations because you need to know the count of these intersections. Well, Bharadwaj here came up with this really neat idea, borrowed from the OLAP world, to use what are called star trees. They're sort of pre-computed data cubes where the idea is that if you know ahead of time, hey, I'm probably going to want to compute sub-aggregations like this. I'm going to want to aggregate across these particular dimensions. You specify that when you create your index, and then as you're ingesting stuff, it builds out this star tree that pre-computes this stuff for you, which is pretty nice. Because then at search time, you just go and look it up in the star tree. Great. Another idea is, why not learn from the database people? Why not build a proper query engine? So everything I've talked about today is operating at the shard level, where Lucene does very well. But what about the layer above? Right now our coordinators are fairly naive, right? They just, a request comes in, they just fan them out to shards, and then they coalesce the results. What if we could say move some of the computation up to the coordinators, and then scale them separately? Maybe move some of the aggregation work up to the coordinators. Maybe we can execute joins in the coordinators. So this is all fairly exciting stuff. And once you start having this distributed computation, you can build query plans and optimize those query plans. So this will probably be a slightly longer term project. I'm glancing over at Pallavi, so that I'm hoping she doesn't mind me saying that it's going to be slightly longer term. But yeah, we're doing our best. Another area. Oh, oh no, I put up the wrong picture. This is actually supposed to be a link to a pull request from Anikit. If you go search on GitHub Lucene and search for the number 21 in active pull requests, Anikit made this great proposal to the Lucene community to change the way that doc IDs are stored in those leaf nodes. It's not a revolutionary improvement. Like, it's not speeding things up by orders of magnitude, but hey, it's a 10% speed up, and it also reduces the size of these doc IDs by about 10%. So that's very exciting. I sincerely apologize to Anikit for not linking to his PR here, but yes. Go check it out on Lucene. It's an open PR. If any of you are Lucene committers and you can look at Anikit's PR and comment on it and maybe merge it, it's a nice improvement. So I technically just hit time, but maybe we can do questions.